This was one of the most challenging questions in A-level maths in June 2022. In fact, less than 1 in 20 students scored full marks in Part A. But don't worry, I'm going to help you out with it so that you can feel confident if one like this comes up this summer. Let's take a look at Part A. It says Figure 4 shows a sketch of a Ferris wheel. It says the height above the ground, h, meters, of a passenger on the Ferris wheel, t seconds after the wheel starts turning, is modelled by this equation, where a, b, and alpha are constants. Figure 5 shows a sketch of the graph of h against t for 1 revolution of the wheel. So we can imagine that a passenger maybe gets on here and then the wheel starts turning. They increase in height until they get to the top of the wheel, and then the wheel continues turning and they come back down here. It says, given that the maximum height of the passenger above the ground is 50 meters, the passenger is 1 meter above the ground when the wheel starts turning, and the wheel takes 720 seconds to complete 1 revolution. For Part A, find a complete equation for the model, giving the exact value of A, the exact value of B, and the value of alpha to 3 significant figures. Let's consider how we can build this equation for h from a series of graph transformations of the parent graph, the base graph, which is just going to be sine of t. I'm going to call that parent function sine of t, f of t. Now, what's the first graph transformation that we could apply to sine t to get closer to this? Well, one thing that we could do is to think about how we can get this plus alpha here. Notice that that plus alpha is inside the bracket here. So I'm going to replace the t inside the bracket with t plus alpha. So every t here gets replaced with t plus alpha. That's going to give me sine of t plus alpha. And I'm going to call that new graph g of t. So g of t is this function here. Next, I'm going to think about how I can get the bt in this position. Well, I'd want to replace the t that we have here with bt. So I'm going to do g of bt, because that will replace every t in this equation that we have here by bt. How can I get the a outside of the brackets here, outside of these brackets? Well, because it's on the outside, I need to multiply on the outside of the brackets by a in this position. So I'm going to multiply h of t, which is what I've got here, by a. That's going to give me a new function, this thing, which I'm calling I of t. Finally, what do I need to do to I of t to get the graph that I want? Well, I'm missing the modulus signs on the outside. So I need to put modulus signs on the outside of I of t. And that final function, which I call j of t here, is exactly the graph that we have in the question. Let's consider these graph transformations from a graphical perspective. How does it actually affect the graph? Well, let's start by sketching the parent function sine of t. You should know what that looks like. It looks like this. Notice that the amplitude of this graph, the height here, is height 1, and the period of this graph is 360 degrees. The graph repeats itself every 360 degrees. If I do f of t plus alpha, so if I take this graph and apply this transformation to get sine of t plus alpha, what would that do to f of t? Well, I'm adding alpha inside of these brackets. That means that it's going to affect the x-coordinate, here the t-coordinate, but in the opposite way to you might expect. It looks like it's saying that we add alpha, but in fact, we're going to subtract alpha from each of the x-coordinates. In other words, each of the t-coordinates. That means that the graph will have been translated by alpha units to the left. So every point on the graph will have moved alpha units in the leftward direction, horizontally. We say that this is a translation alpha units to the left. Notice that this doesn't affect the period of the graph. It's still 360, nor does it affect the amplitude. If I call that graph g of t, and now I apply the transformation g of bt to that, how would that affect the graph of g of t? The transformation is happening inside the brackets. That means it only affects the x-coordinate, the t-coordinate here. And in the opposite way to the way it says. It says that it's multiplying by t, but in fact it's going to be dividing all of the x-coordinates, all of the t-coordinates, by b. So what's that going to mean about our graph? Well, in particular, here, the period will also be divided by b. So the period's no longer 360 degrees, the period is 360 divided by b. Note that this only affects the horizontal coordinates, so this amplitude will remain as 1 under this transformation. If we call that graph h of t, what would multiplying by a on the outside do to this graph? Well, if we multiply by a on the outside of these brackets, it's actually affecting the y-coordinate, the h-coordinate in this case. And it does what it says on the tin. We're actually multiplying all of the y-coordinates by a. So that means that the amplitude of the graph, which was 1, now gets multiplied by a. 1 times a is a. So the graph gets stretched parallel to the vertical y-axis, the h-axis, by a scale factor of a here. If I call that graph I of t, what would the modulus of I of t look like in comparison to the graph of I of t? Well, any parts of the graph that were below the horizontal x-axis or t-axis will get reflected in that x-axis, so they're now above the horizontal axis, so that all values now have a positive y value. So you see that we get this part of the graph is unaffected, but this part which was underneath gets reflected up to this position. Note that this doesn't affect the height of this graph here, it's still A, nor does that affect the period of the graph. It's still 360 over B. So what we've got here is the graph of h. We can visualize this graphically here on Desmos. Let's start with the parent function sine of t. Next, let's consider g of t being sine of t plus alpha. Notice that as I increase the value of alpha from 0, the blue graph is translated to the left because we're subtracting alpha from each of the x coordinates. Next, let's consider the function h of t, and let's consider what happens when I change the value of b here. As I increase the value of b from 1, notice that the period of the graph gets smaller. That's because I'm dividing each of the x coordinates by b. Now let's have a look at what happens when I change the value of capital A, starting with 1, and then 2, and then 3. You can see that all of the y coordinates have been multiplied by the a value. They've been stretched in the y direction by scale factor a. Finally, let's have a look at the effect of the modulus on this graph. When we apply the modulus, it is that all parts that were beneath the horizontal x-axis have been reflected in the x-axis, and all parts that were above just remain the same. So the graph that we've ended up with here is the graph in the question. So how can we work out the value of a, b, and alpha? Let's start with the exact value of capital A. Well, in the question it says that the maximum height of the passenger above the ground is 50. That's talking about this distance here, which corresponds to this distance here on the diagram. That is capital A. So capital A is 50. If you realise that, you get 1 mark. Next, we can look at this piece of information. It says the wheel takes 720 seconds to complete 1 revolution. Well, be careful with this. That's this interval here on the t-axis. So from here to here on our graph, that's half of 360 over b. So that's 180 over b. So 180 divided by b is 720. If we rearrange, we get this. So to find b, all you need to do is 180 divided by 720, which is a quarter. That gives you your second mark. We can replace a equals 50 and b equals a quarter into the original equation that we were given to get this. But we still need to find the value of alpha. How can we do that? Well, there's only one piece of information we haven't used. That's that the passenger is 1 meter above the ground when the wheel starts turning. So that's really talking about this height here on the graph. When t equals 0, h equals 1. So if we replace t with 0 and at the same time replace h with 1, then we end up with this equation. Notice that inside the bracket there we have 50 sine alpha. Notice also that we're dealing with this part of the curve here, which actually was not part that got reflected, it was part of the graph that remained the same under this final transformation, taking the modulus. So essentially we can just say, well, the modulus of 50 sine alpha is just 50 sine alpha for that part of the graph. Therefore, sine alpha is 1 over 50. Apply arcsine, we get this from the calculator, make sure you're in degrees mode to match the question. And then we need to round this value of alpha to 3 significant figures, as it says in the question, so 1.15. Finally, we need to make sure that we write down the complete equation for the model. So substitute this value of alpha as well back into here to get the final equation for the final 4th mark. Part B. Explain why an equation of this form, that looks very similar to part A but with a plus d, where d is a positive constant, would be a more appropriate model for 1 mark. Well, notice with the original model that, in fact, the height of the passenger above the ground actually reaches 0. So the passenger would kind of be scraping their legs along the ground, if not worse. So we could say something like the minimum height above the ground of the passenger on the original model was 0 meters, which obviously isn't realistic. That gets us a mark. Or you might say something like adding d means the passenger does not touch the ground. Any equivalent wording to either of those two things will get you the mark. In their report after the exams, the examiners said that this was a challenging question for the majority of candidates, with very few scoring all 4 marks in part A. For those that attempted the question, so they're implying that many didn't even attempt it, most scored at most 1 or 2 marks. They said the final mark of part A was scored very rarely. At less than 5% of the cohort, so less than 1 in 20 students got full marks for part A. They said the second B mark, for finding a value of b, was very poorly answered, with many not realising that a simple calculation was needed. So many students overcomplicated it. How would you have tackled that question? Do you think that you would have scored full marks? And having watched the video, do you think that you would now score full marks this summer? Have you got another way of doing it? Let me know in the comments and let me know if there are other topics you'd like me to review in future videos.